Welcome to the AFMS seminar today, and it's my pleasure to introduce Hessam Babaee. He's currently assistant professor at the University of Pittsburgh. He received his PhD in 2013 from Louisiana State University. And after spending some time at MIT as a postdoc, then he joined the University of Pittsburgh in 2017. His main research area is reduced order modeling and machine learning for fluid flows. Title of his talk today is On the Fly Reduced Order Modeling via Time-Dependent Basis. So please go ahead.
Sure. Thank you so much for the introduction, and thank you for inviting me. Yeah, my name is Hessam Babaee, and I'm an assistant professor at the University of Pittsburgh Department of Mechanical Engineering. So I just want to acknowledge my students and postdocs who contributed to this work. They're listed here. And also the funding sources from NASA, Department of Energy, NSF, and Air Force Office of Scientific Research. So the topic of this talk is reduce order modeling with time-dependent basis. So I just want to draw your attention to this animation here. This is a jet that is coming from left to right, and this is a chemically reacting flow with 23 species. And so if you want to solve this kind of flow, you would have to solve a separate PDE for each of the species. And this is 23 species, so we have combustion problems where we have actually large number of species, and tracking each one of these species could become computationally intractable. For example, for large fields when you have like 1,000 species. And so the idea is that how can we exploit the structure, coherent structure in these systems to reduce the computational cost. And I'll show you today, actually, with time-dependent basis, we have made some progress, and I just want to show you some of those results. And so this is a motivation example. This is the outline of my talk. I'll just talk about motivation for time-dependent basis and some overall description of it, and then I'll talk about two applications of time-dependent basis. One is for the example I was just talking about, reducing the cost of passive and reactive species transport equation, and the other one is for the application of this reduced order modeling for computing sensitivities in reactive flows. Or it could be also a non-reactive problem as well. And so let me just talk about reduced order modeling with time-dependent basis. So the motivation is that if you have a high-dimensional PDE, let's say this del V del T is equal m, where x is the number of dimensions, could be parametric dimensions, could be differential dimensions. We typically write the solution of these PDEs with separation of variables. So we take time out and say, like, this is a time component, and then we choose the basis. And the basis is perhaps the most important decision we're making them when we do scientific computing. So if you look at the spectral methods, finite difference, finite element, finite volume, they all are primarily identified by the choice of basis made in each one of them. What happens if we choose this basis from this library is that they disregard any sort of correlation in the solution. And so that could be seen as the reason why these methods suffer from the curse of dimensionality when this dimension is high, if you just use this kind of basis. And so perhaps the only generalizable way to beat the curse of dimensionality and computing when you have high dimensional space is to use correlation. And so reduced order modeling is one way to extract this correlation and enable this kind of computation. So this is a typical workflow of reduced order modeling. So you have your high dimensional PDE, and the applications could be on-static quantification, combustion, or you can have Fokker-Planck type equations. To reduce this, you would have to first gather high fidelity data on this PDE. Once you gather the data, then you can look at the data. It could come from the data could come from simulation or experimental data. Then we perform dimension reduction. Examples like POD, DMD, autoencoder, decoder, and then once we have that subspace, and the presumption here is that these high dimensional PDEs, they have an intrinsic dimensionality, and once we find it, we can go back and project the equation onto that low dimensional subspace, and then solve the equation in that subspace. So then that's where you build your ROM or reduce or model. But there are problems with this workflow that I want to highlight here, is that so when we gather data, there's no guarantee that when we change the operating condition, let's say we gather data for some Reynolds number or Mach number, we change them, then the reduced or model that we built with the existing data would work for the new operating condition. So basically, we can say these reduced or models do not necessarily extrapolate. And the whole process of generating data could be actually an enormous task. Probably not for 2D or 3D PDs, but for problems that are like 10-dimensional or 100-dimensional, we may not be able even to generate the data, because we would have to solve the full dimensional problem in the first place. And we cannot solve that problem. And so probably that's why we want to do reduce or modeling. Also, they have, especially for high dimensional problem, the I/O storage cost could be enormous. And so that's another issue. And there is more fundamental issues that when we look at these problems, especially for turbulent flow problems, they have really high dimensional, even intrinsic dimensionality. And so just approaching, doing reduced or modeling for turbulent flow using static manifolds, such as POD, has fundamental difficulties in capturing these high dimensional problems. And especially, for example, it's hard to capture problems that are highly transient, like rare events, using this type of reduced order modeling. So, so this is the motivation for reduced order modeling time-dependent basis. At the very high level, we look at the same PDE, but we do separation of variables, but not in time. So if you notice here, the basis is time-dependent, and so this is perhaps the main distinction between classical techniques, scientific computing techniques, or reduced order modeling techniques, that this is now also time dependent. So there's time here and time here. So basically, we don't choose these bases from a library. We let the physics of the equation to derive these bases. And so this is, so basically, you can look at these bases, physics informed time dependent basis. And the way we derive this evolution equation for these bases, they will capture the correlation in the solution of this system on the fly. And so this framework is not data-driven, although it could be extended to data-driven settings. But what I'm going to talk about today is purely model-driven. That means that we don't generate any data to begin with. And so we just go and directly replace this into the governing equation here, and we derive evolution equation for this and the modes as well. And so that way allows us to bypass the whole data generation process and all the issues and limitations attached to it in a typical data-driven reduced order modeling. And so, and because these subspaces are time-dependent, you can actually solve some particular problems in a really elegant way. For example, if you have these highly transient instabilities. And so this is a big picture overview of time-dependent basis. So let me get to particular examples, and I'll show you within each of these examples how you can actually derive these evolution equations for the time-dependent basis and different flavors of it. So the first example is turbulent combustion. So this is, so I want to draw so let me just explain the equation. So in turbulent combustion, you will solve the compressible Navier-Stokes equation as listed here, and then you would have to solve this species transport equation. So this phi k so k is phi k is the species concentration mass fraction, and you can have order of 1,000 species for complex fields. So you would have to solve 1,000 PDEs coupled together. They're all transported with this turbulent velocity field. So obviously the computational cost could be enormous, just the flops, and perhaps more important than flops is the memory and I/O constraints associated with solving this problem, because you would have to store this large number of species in the memory. And especially for extreme scale computing, that could be problematic because memory limitations are more severe than flops limitations. And so typically what is done is that instead of solving, let's say, 1,000 species, a skeletal model reduction is done, and then a smaller number of species is chosen. So basically, some species are eliminated. A lot of them are eliminated. And so that could be a major source of error. Because it's extremely difficult to know which one of those species you have to, some of them are clear, but not all of them. So I want to just draw your attention to this quote from this group at DOE, that as of now, even with these fantastic supercomputers that we have, the I/O limitations, input-output limitations of data storage allows us to store every 400 time step of the solution of this type of DNS of combustion. Whereas you have phenomena, highly transient intermittent phenomena that happen in the order of a 10 simulation time step. So if you store every 400 time step, this is just on the I/O side of it, you can completely miss that highly transient phenomena. So how can we reduce this cost? And so that's why we are using this kind of reduced order modeling as I talked about. So this is just a sort of a graphic visual is the illustration of the method. So so this is, instead of solving for these NS species, and you can think of NS as being a large number, we solve that using a set of orthonormal time-dependent modes. So these are orthonormal modes. So you can think of this as bases in the physical domain. And then you have this sigma matrix, which is, so this is an SVD-like decomposition. And I'll show you the connection actually to SVD, but this is instantaneous SVD. And so this is the matrix of singular values. It has to be diagonalized, but this is actually a full matrix. And these are a set of orthonormal vectors. So each row of this matrix is an orthonormal vector in the composition space. So instead of solving for these NS species, we solve, which you have to solve NS coupled PDEs together. We solve for R PDEs coupled together, and we derive ODEs for each of these two components. So to just, if we can accomplish that, and if this is an approximation of this, because so there is an error associated with this, which is a reduced order modeling error. But if this error is small, then instead of transporting large number of species, you can transport a smaller one. And so you can reduce the I/O and memory and hopefully flops by doing so. So and so in that sense, these are time-dependent bases here, and these are also time-dependent bases. These are time-dependent bases in the physical or spatial space. These are time-dependent bases in the composition space, which is where the reactions are happening. So each of these columns are concentration of one species. So let's say this is hydrogen, oxygen, and then the corresponding column in this vector are actually the same. Shows the concentration, this new coordinate system of the same species. And so you can always go back to the full dimensional, but in the computational workflow that we have, you never have to form this multiplication of these three matrices. So you would solve for this and this and this in a compressed form. So like I said, this is separation of variables, but not in time. So we took out space, but not time. And the way we derive evolution equation for all these three components is based on a variational principle that I will show in the next few slides. And so, and based on that variational principle, the minimization of that variational principle leads to the evolution equation of all these three components. And like I said, this is based on time-dependent basis. So this assumes that the low-dimensional manifold is nonlinear and very high-dimensional. But what we do, we tackle that by evolving the subspace that we have. And so this subspace is always adapting. And so that's how it can actually reduce the dimensionality of a high dimensional system. And like I said, there's no data required. So we'll derive an evolution equation. So we extract this not from doing any DNS or generating any data, but we derive evolution equation for this. So that expensive part of data generation is just completely eliminated. The other nice thing is that because there is no data, these low rank approximation can adapt to the operating condition on the fly. And because of this nice SVD like structure that it has, the modes, the special modes, U and Y, both of them are highly interpretable. And so this is the overall framework. So let me just get into the details. If you just write the equation that I was showing it pictorially in the previous slide. If you just write that down mathematically, you have this expansion. And so you have this error, which is the reduced Ermolling. We call this DBO, which stands for dynamically biorthonormal decomposition. So this is orthonormal, this is orthonormal. And so that's why this is biorthonormal decomposition. I'll talk about the dynamically part of it as well. So if you write the species transport equation, take everything in the right-hand side and call that M. Here you have the transport, this is advection, this is diffusion, and the chemical sources to the right-hand side. And this is the variational principle I was talking about. So we look for time derivative of time-dependent subspaces and sigma and time-dependent subspaces in the composition space, such that they minimize this dysfunctional. So what is dysfunctional? This is the rate of change of this reduction minus, so this is the del by del T of this reduction minus what you have from the full dimensional model, which is the rate of change of the full dimensional case. But here, instead of phi, we replace it with this expansion again. So this phi is replaced with this expansion. And once you take the write down the first order optimality condition with respect to U dot, sigma dot, and Y dot, you get closed form evolution equation for all these three components. Let me also say that the way this is formulated, this is looking for the best update in your subspace, U and Y, and their coefficient, such that this is minimized. And if you solve this problem, you don't need to do iteration, you just need to solve PDEs and ODEs. So this is the these are optimality conditions of this variational principle. So for the U equations, which are the special modes, so this U is U1, U2, all the way to UR, you get this set of PDEs, which has actually, if you look at it, it has all the structure of the original full dimensional equation. And you get two ODEs for the matrices. And so what you see here, this is not actually, this is a projection, but this is a projection to the complement of U. So whenever this right-hand side is within the space of U, these modes won't evolve. But whenever the right-hand side goes outside of that space, it'll trigger evolution of these modes. So they have this built-in adaptivity that will chase the solution wherever it goes. And that shows up in the Y basis as well. And the sigma is simple projection onto the U and Y. So more details of this is in this paper. But let me just compare this to what is commonly done in the field of combustion, which is a data-driven reduced Ermolling based on principal component analysis, which I've shown here. In that kind of reduction, you write down the species as a set of spatial modes times some orthonormal vectors, which is in the composition space. Here, this part, this is a static subspace. This static subspace is found by doing a DNS. You first perform a DNS and then perform an SVD. So you find the low rank subspace from there, and then you plug it in here. So this is known from data, and then evolution equation for this is derived. So, but here, like I said, this is also time dependent as opposed to static here. And so this is really the main fundamental distinction. The other thing is that this is, like I said, this is not data driven. This is what we call it model driven time dependent basis. Okay, so, but this is not commonly done in combustion, and I'll compare some of the results against that, so we'll see that. So going back to the problem, I was just talking about my first slide. So instead of solving this system, we solve for here 5 modes. I'm just showing the first 4 dominant modes. here this is a movie. I'll play this in a second. This is a singular value obtained by this reduced order modeling. And what we do, we go back and do a DNS for just the comparison purposes. And at each time instant, we take an SVD, because that would be the optimal basis instantaneously that we can have. And so if we do well, we will recover that instantaneous SVD, or we call it instantaneous PCA, IPCA. And so you will see the comparison. So these are the full dimensional equation. Instead, like I said, we solve these. So these all three components of the reduced order modeling are shown here. So we are capturing the dominant singular values very closely. So the line is actually DBO and the circle is instantaneous PCA. And these are the modes. So if you see, the first mode captures the larger scale structures, and as you go down to higher modes, you capture finer and finer structure. But here the modes are also evolving with this system, and so does this Y coefficient. So this Y coefficient, Y matrix, each column is an orthonormal vector, and so collectively they represent a time-dependent subspace in the composition space. And so I'll show you some of the error plots for some of the cases that we have done, but let me just stand back here and just give you a little bit overview of the genesis of this time-dependent basis, which was done for a UQ problem. I'm not going to show any UQ results here, but I just want to acknowledge what has been done before, which is to solve a UQ problem where X and T are a space and time, and this psi is a random space, and this was done for the decomposition of that random field to a random processes times the modes. So there are various flavors of this bi-orthonormal decomposition and dynamically orthogonal decomposition, and they have been shown to be equivalent to each other. And later, I worked with Themis Sapsis and George Ganidakis to extend this to linear systems. So with Themis Sapsis, we worked with extended it to linear system. We applied this kind of decomposition to capture transient instabilities. But like I said today, I don't want to talk about these topics, but there are various flavors of this time-dependent reduction. And so whenever this is applied to linear system, we call it optimally time-dependent decomposition. So let me go back here. So I'll just go back to the species transport equation. So this is the overview of that formulation. And here, like I said, the modes are orthonormal in a space instantaneously. So this is the integral of the modes, the projection of the inner product between two modes and the inner product between the vectors in the Y coefficient. So I want to show you some more results on the passive transport equation. This is, let's say the velocity field is here advanced by Berger's equation, which has shocks, and then we have 1,000 species. But these species have different diffusivity, and we just chose this one. So they are actually order of magnitude different in the diffusivity. And here we solve this system. So we're just showing the concentration of phi1 to random on phi1 and 800 with different reduction orders. So instead of solving this 1,000 PDEs coupled together, here we solve with only two modes, which is 2 PDEs, and then the rest of them are ODEs, which are not so expensive to solve, then 4 PDEs and 8 PDEs with this reduction. And you can see we quickly converge to the truth here. And so this is one snapshot in time. Which shows actually you can quickly recover this solution with much less number of modes or equivalent number of species. And here we compare the modes, the orthonormal modes, with instantaneous PCA. Like I said, instantaneous PCA would be the optimal set of reduction you can have. That means if you just generate the data, at each instant of time, take a PCA. So that would be data driven. We go back, and once we compute these modes, we compare those modes against IPC, and here we show actually we recover IPC. The first two modes are shown here. And here, this is an error convergence plot where when we add more modes, we show that the error is quickly decaying. And this is the error, this is the Frobenius norm between all species, computed in full dimensional case and computed in the reduced form. And here we show that the instantaneous singular values obtained by this reduced order modeling captures the leading instantaneous singular values of PCA. So again, for IPCA, you would have to solve the full dimensional case to be able to generate that plot. We never solve the full dimensional case in the reduced form. In the reduced form, we just solve for the modes and their coefficients. And so this is just a simple problem. Now I'll go to a more realistic problem. And these are actually some new results. So this, let me just quickly skip that. So I want to show you one more comparison between the case that I was showing for incompressible reactive flow. This is phi1 concentration compared, this is the DNS, the full dimensional case, and this is the reduced order modeling case. You can see actually they closely match each other. And this is another species, this is the 10th species. At different times, each row shows the mass fraction at different times. And you can see they match pretty well. So this is, once you solve this in this reduced format, you can come back to the full dimensional case and reconstruct the full dimensional case. And I showed a video of this. Here I'm just showing snapshots of the modes at different times. Again, as you can see, the first mode captures the largest scale structures, and as you go to second mode and third mode and fourth mode, capture finer and finer structure. The other thing to notice here is that this is a jet going from left to right. As the jet evolves, the modes are also evolving with that jet. So the jet goes forward and then the modes are evolving with that and covering that. So if you're familiar with POD has problem with convective problems. But here, because the subspace evolves, we evolve with the system, and so that issue simply doesn't exist yet for time-dependent basis. So this is now a compressible flow case. So this is with 11 species and 21 reactions for syngas model. This problem has extension and reignition, and so it's a highly transient problem. So we apply this reduced order modeling to this system, to a two-dimensional case and a three-dimensional case. So this is a two-dimensional turbulent flow, and this is a three-dimensional turbulent flow. And so in the two-dimensional case, here I'm just visualizing the modes here. And this is just a full dimensional flow for a reference. So you can see again, these are orthonormal modes, so they are instantaneously orthonormal. So these are the time-dependent bases. And you can see the first two modes capture the larger scales, and the third mode captures these finer structures in time. So here, I'll show you the results with different reduction order. Let me just show you the 3D results as well. So for the 3D results, the first column here, this is just a mixture fraction from found, which is a full order model. So this is just for reference where the flow is. And each row corresponds to a particular time. Now, if you solve this for the three-dimensional problems, the modes are also three-dimensional, the spatial modes. And here you can see, now this is the state of the flow, and the modes are following that flow instantaneously. And as the flame evolves, so do the modes. And like I said again, if you look at it here, this is this first mode is associated with the largest instantaneous energy, and the second column is associated with the second largest instantaneous energy, and so on and so forth. So that's why you capture finer and finer structure and go to a higher number of modes. let me just show, these are all qualitative results. Let me show you some quantitative results. So here, this is an RMS comparison. This is for reduction order 4. Remember, we had 11 species, and we also here include the energy equation as another species because it has the same form equation. So going from 12 to 4. And let me just remind you, this system is already reduced to the maximum possible to the 11 species. And so that's why any further reduction is gain. And we have recently applied this to a more detailed mechanism with 53 species, and we could reduce that with a small number of modes. But here I'm just showing the results for R equal 4. And you can see we can actually do a relatively good approximation of the DNS. So this is the mixture fraction comparison with DNS, the mean value and the RMS value. And so this is temperature, the mean value and RMS value compared against the DVO reduction with order 4. And so this is a scatter plot of all points in space and time of DNS versus DVO. So you see the mass of the points are actually aligned here with this line, which is y equals x, which, so you have also this, the error here as well. But if we increase R from 4 modes to 5 modes, see a much better result. And then the scatter plots are actually converging as well. And so if you do R equals 6, you get, so this shows, so if R is equal to NS, we recover the full dimensional equation. And there is no reduced or modeling error, and all the DB equations go back to the full dimensional case. But here we show R equals 6. This plot shows us how, first of all, this is a proof that this system is actually, even though the flow is turbulent, and if you just look at it, it may look, it is extremely high dimensional, but if you just look at it through the right angle, you can extract the low dimensionality. So these plots actually show the low dimensionality. Let me explain that. These are the instantaneous singular values obtained by PCA, which is data-driven, compared against that of DBO. So if you do R equal 4 DBO, we only have 4 modes, and we can compute the SVD of that sigma matrix that we have. Those are plotted here. They're compared against those obtained from IPCA. As you can see, the first 2 modes, this is with R equal 4, are captured really well. And these 2 modes capture more than 99% of the energy for this system. This is a log scale, so these other modes don't carry that much energy. And this is, so we are not able to capture the last modes, which is always the case. You want to capture this one, you need to add another mode. And when you add another mode, you also capture this one well. So this is with R equal to 5. And you even improve the accuracy in the 3rd mode. So you can see here. And if you go to R equal 6, you improve even further, and R equal to 7. And so this shows this fast decay of the instantaneous singular values. This shows that this system, if it's looked at through the instantaneous reduced or modeling, is actually low dimensional. You can exploit that. So here we have done the PCA as I was talking about. So this PCA is a data-driven reduced order modeling technique where you first do perform DNS, you collect the data, space-time data, you store it, and then you perform SVD, and then you can extract this low-dimensional subspace, which is a static. So here the blue is PCA, and this is a movie that I'm gonna play. And so this is what is extracted by this model-driven dimension reduction. And we always show the IPCA because this is the optimal. So if you track IPCA, that means we are actually approximating the optimal basis here. And as you can see, so the PCA is not changing in time because that's the static here. These bases in the composition space are actually changing in time, and the DBO is closely approximating the instantaneous PCA. But it also shows, this is the interpretability of this reduction, is that This is the first mode. So this is the most important mode. So basically what it does is the way to interpret this mode is that instead of doing a skeletal type reduction where you actually eliminate a species, it's better to take a time-dependent linear combination of all species and form a new species, if you want to name it that. And so this is a weighted time-dependent linear combination of existing one, and this is you can name that as a new species and solve this species. So that's another way to look at it. So you can say that this linear combination is the most important linear combination among that species. And so if you go to Y2, this is the second mode, then you can see actually there is more time variation in the second mode compared to PCA. And again, IPC and DBO approximate each other very closely. And if there isn't a species that doesn't have any footprint in these Ys, perhaps you can eliminate that. But there is really no need to eliminate any species up front, because you don't pay as much cost by just adding a new species here. So you're always solving this reduced form. Okay, so now I want to switch gear and I want to show you another application, which is computing sensitivities using this time-dependent reduction. Let me just set the stage here. So if you have an evolutionary system and you want to compute sensitivities with large number of parameters, here I'm showing alpha 1 to alpha d as the design parameters, that you want to compute the sensitivity of that system with respect to this parameter. You have two choices. You can either solve the sensitivity equation for each of these parameters. So that you would have to solve the forward sensitivity equation. And for chaotic systems, these sensitivities would blow up. Or you can just solve one forward equation, store the solution, and then solve the adjoint equation backward in time. So that would require I/O. Heavy I/O, because you would have to store the solution here of the nonlinear system and then read that back when you go back. And so again, for this extreme scale computing architectures, this is problematic. So the way we see this problem, instead of, we are not going to do the backward because that requires I/O. We want to solve forward equation, but instead of solving for each one of these PDEs, we expect the instantaneous correlation between these sensitivities and solve this in the reduced format using time-dependent basis. So the idea is to use the correlations, to use the instantaneous correlations between these sensitivities and solve this system forward in time in this reduced format. So this is schematically. There's a little bit of a difference between this and what I showed for the reactive flow problem. So this is your nonlinear equation, and this could be all the number of design parameters you're interested to compute the sensitivity of this system with respect to. You can take the derivative of this system, so this is the linear sensitivity equation. So instead of solving for these D columns, we want to solve these with these R orthonormal modes. And here, this has only two components. You can actually do a triple component here and have a sigma and Y, and the two of them are actually equivalent, and we have shown that. But here we take this simpler form, which is consistent with OTD, optimally time-dependent decomposition. So we call this method FOTD, which stands for forced optimally time-dependent decomposition. Again, there is a paper here, which is going to appear in SIAM Journal of Scientific Computing soon, but it's already on our archive, so you can find more details of what I'm showing you here. And so you can form the variational principle, derive closed form evolution equation for these modes and their coefficients. Again, no data-driven approach. So this is a very simple demonstration of this for an ODE. ODE, let's say here I have alpha 1, alpha 2, alpha 3, these three coefficients of this lossless system that I'm perturbing. So, and here, what I'm showing you, this is an animation. This is a U1 and this is U2. Instead of solving this three-dimensional system, I solve it with the two-dimensional problem, which is this time-dependent plane. So this is a time-dependent subspace, and these are the coefficients of this. You can see actually this subspace evolves as it sees changes in the system. And especially when you get to this kind of, you can think of this as a transient instability, these bases adapt to that change in operating condition. And so that's why effectively provides a reduced subspace for this otherwise three-dimensional system. So this is a small demo. I go back to the problem I was talking about, the same reacting flow problem. Here, we are interested in computing the sensitivities of these species transport with respect to all reaction parameters here. So these reaction parameters, sensitivities of these are extremely important because if computing these coefficients are expensive, and a first order analysis is that to know which one of them affect the solution most intensely. And so if you want to reduce the uncertainty, you want to go after those parameters. And also for skeletal model reduction, these are also used. So this is actually a massive problem because you have, in this problem, we have 34 reaction parameters and 23 species, and they're all coupled to each other. So if you perturb one of them, it will affect all other species. So overall, we have 782 sensitivity fields. And the way we can look at this, it can be represented by a tensor, where the direction of the tensor are grid points, and this direction and this species and this direction are parameters. So these are the full sensitivity tensors. We could have had one set of modes for each of the species, but that's not, but these species are also still correlated with each other. So instead of that, we flatten this tensor and we look at this as a matrix and use this reduced order modeling and have one set of modes for all species and all parameters and their coefficients. So these are color coded. So this is the red here, for example, shows the sensitivities of the second species. And so if you want to even solve adjoint equation here, you would have to solve 23 backward adjoint equations. Because for each species, you will have to solve one adjoint equation. So instead of doing this, we solve this in this reduced format, and we extract the instantaneous correlations between different sensitivity fields. So these are the first most sensitive modes and second most sensitive modes. And here again, we compare against the SVD of the full dimensional case, and we see we really nicely track the dominant singular values. And with 5 modes, the overall error between all sensitivities is less than 1% in the evolution. So this is the error obtained by instantaneous SVD, which would be equivalent of IPCA, as I was showing in the combustion problem. And this is with FOTD. And so basically here, we saw 5 PDEs instead of 782. That's really the bottom line. And this Y matrix shows you the coefficient. So this shows the error percentage for different reduction orders. As you can see, with order 2, we are order of 5%, 6% error. And the optimal one shows that obtained by instantaneous SVD. That's the best we can do. That's sort of the lower limit of the error we can do. And we are so following that, means we are following the optimal reduction here. And so as you can see, article 8 captures that. But this also shows, this is instantaneous singular values, shows that this system is indeed low dimensional in this basis. And so this axis is the percentage of the energy captured, and this axis is singular values. So with 2 modes, we are almost around 99.9% of energy of the all sensitivities. And with 5 modes, we are almost near 100%. You capture 100% of the energy. So this is, but if you were to formulate this with like a POD type modes, you would need a significantly large number of modes, and that would be a data-driven reduction and so on and so forth. So this is again a snapshot of the modes at different times. These are sensitivity modes, right? So this is the first mode, second mode, and third mode as time. And so this is T equals 1, T equals 3, and T equals 5. And so so this will tell you where the sensitivities are. And again, they capture fine and finite structures as you go to higher modes. The Y coefficients here are immediately interpretable. So here the Y coefficient, each column of this Y matrix has number of species times number of parameters. So this is like 782. Each column is 700. It has 782 components. You can reshape that with number of species times number of parameters. So this vector just reshaped to a matrix. And this is the second column. And you can immediately see, for example, the way to interpret that is alpha 1 affects the second species most intensely. And so this is the degree that is affecting that. And so this is the first mode. So this is associated with larger energy. You can go to the second mode and see finer and finer structure here. And the second alpha is not affecting any of these species. This is not zero, but this is much smaller than the first one, and so on and so forth. So this matrix is easily interpretable. And with that, I'm just going to conclude and see if you have any questions. So, we can take this framework and solve these problems that are either high dimensional or large number of PDEs coupled together that need to be solved. And instead of solving the full dimensional equation, we solve these equations in this reduced form without the data. And so for sensitivity, we showed actually you can compute sensitivities in these evolutionary systems with respect to large number of parameters with surprisingly low number of modes. In our paper, we have several other examples that you can look at. And we have seen these structures in different types of problems. And so there is a neat, which I didn't have time to cover that. There's a neat connection between this FOTD and finite and OTD and finite time Lyapunov of exponent and dynamical system and transient stability. Those papers are, I referred to them at the beginning of my presentation. So there are really neat connections between dynamical system theory. And so I'll just go quickly over the rest of them. Perhaps the most important reduction we do here is in terms of memory and storage. So we always solve this equation in this compressed form. You can multiply these matrices and have the full matrix, but you don't have to, and you can always solve this equation in this compressed form. And so that allows you to reduce the memory and IO demand. Then you can store them in this compressed form. Then you can go back and reconstruct them. So that allows you to solve these equations in this reduced form. So just in the interest of time, I'm just going to skip the other items and acknowledge students postdoc in my group and open the floor to questions.
Yeah, thank you very much, Hessam, for a very interesting talk. So if you have a question, just unmute yourself. Yeah, it's very surprising that you only need 5 modes for such, gigantic PDEs. Is it important to assume that there are many similar PDEs, or is it possible to use this method for many different PDEs?
So I know I focus on the reactive flow problems because these are fascinating and computationally expensive. But I can sort of intuitively explain why we can actually solve this with 5 modes. Like this is actually 782 field variables, and we can solve them with only 5 modes. Is that all these sensitivities are all advected with the same velocity. So if you look at them instantaneously, they have very similar shape. Or what we say, they are highly correlated instantaneously, not in time. If you look at them in time, they're actually, they decorrelate very quickly. They become actually extremely high dimensional problem. But if you look at them instantaneously, these different sensitivities, they have a large degree of correlation. So that means they don't span the full dimensional space instantaneously. They span a much smaller subspace. And what we have shown is that these modes closely approximate the instantaneous SVD. So that means if the system is low dimensional instantaneously, then these modes can capture that. And so, and if you look at sensitivity, so this is more like physical and intuitive explanation. Even if you don't have velocity, you have a generic nonlinear ODE or PDE. Oftentimes, a lot of parameters that you're perturbing, they're not that important. And so there is like a linear combination of parameters that are important. And so we have seen that in system after system for linear sensitivities, you see a high degree of correlation. If you take, let's say you take a steady state, let's say the linear system is a steady state, L is a steady state. So asymptotically, they're explained by the eigenvalues of your L matrix. So we know those systems are low dimensional if there is separation between eigenvalues of L asymptotically, because they are differentiated from each other by exponentially in time. And so we know those systems. So we have some theoretical results in terms of sensitivity that back this up. And so it's just looking at the problem through the right angle allows you to reduce it effectively with these spaces.
Mm-hmm. Yeah. So when we have, I mean, sometimes when we change the parameter, sometimes the dynamics changes quite in a catastrophic manner.
Mm-hmm.
Do we need some special care for that case?
So when we're talking about sensitivities, we are just changing these parameters infinitesimally, right? Because we assume just extremely small perturbation. If you were to change these parameters in order 1, like not just infinitesimal, then you can actually have the subspace could become much more high dimensional than what we have. Mm-hmm. But here we are changing these parameters only infinitesimally. So we are perturbing those, and basically we're tracking the perturbation. So right, in these systems we have seen that the full sensitivity matrix is highly reducible.
I see. So in some sense, you are assuming some continuous dependence of the, I mean, the dynamics with respect to parameter, I guess.
That's right. So you just basically, it's like you have alpha, just do alpha plus epsilon, and just look at the difference of the solution. That's really what linear sensitivity is. But then you do it for different alphas, and so you have different sensitivities. But these sensitivities, because they're governed by the physics of the problem, they're not like completely random, right? There is some degree of relevance between these. And so that similarity, which we say correlation, means that they actually have a low rank structure. And if they have a low rank structure, you can do reduced modeling.
I see. Yeah, interesting. So any question from, just unmute yourself and or raise your hand.
I have a quick question, which is just to ask, so you've shown that this is a more computationally efficient way, potentially, of doing these flows. What then is the most computationally expensive step? Is it like every time step when you have to readjust the subspace? Is that computationally expensive? That's
right. So you would have to solve a PDE for each of these modes, right? So that solving the spatial modes is the most computationally expensive part. So these are, you would have evolution. So we have evolution equation for these modes. So did we actually solve PDEs for each of these modes? So, but these PDEs, this cost of solving each of these PDEs is roughly equivalent to solving one sensitivity equation for one parameter. And so
the cost of solving all of them is the same?
Each one of them was. So our mode is like as if, so basically, if you have D parameters and you reduce it to R, you're reducing the computational cost by a factor of D over R, roughly. Because this Y is just reduced over model, and what governs the evolution of this is OD. So you don't really pay that much cost to evolve this forward in time. But the U modes, the time-dependent spatial modes, are governed by PDEs, and you would have to solve PDEs. So the gain in memory and flops here in this sensitivity equation is D over R. So here, if I have 782 species, and if I can solve this by 5 modes, I'm basically paying the cost of 782 divided by 5. So this is, I'm speeding up the computation by that factor.
Okay, thanks.
Of course.
Have another question, but I'll just wait to see if there's anyone
Sure.
else in the audience before I'll
Yeah,
give another question time.
Sometimes the audience are really shy. Yeah.
Maybe I'll just ask my second question, which was about a little bit more generalized question about, you've shown kind of the application here was thinking about combustion, but how easy or hard would it be to kind of apply this to a different fluid mechanics system that sees kind of these reactive flows? So for me, I do a lot of oceanography. So I was thinking about the mixed layer of the ocean, kind of the carbon chemistry that goes on there.
That's right. So we have actually applied this to just non-reactive systems, like just, fluid dynamics problems. So if you, for example, an example would be a bypass transition in fluid mechanics, right? So this bypass transition, we know in subcritical transition in shear flows, we know that you have the role of non-normality and then non-linearity and all of that. So, but how do you want to find a reduced subspace corresponding to that highly transient phenomena? And so this has been recently applied actually at KTH to study those kind of problems, the OTD reduction, to capture a reduced description for those subcritical transitions. So so you can look at, for example, what kind of, so one question is that what kind of forcing get amplified more intensely in a fluid system, right? Which could lead to transition, for example. And so you can formulate that as a sensitivity problem subject to a high dimensional forcing. And so computing that could be, if you want to solve for each possible forcing, could be computationally an enormous task. But if you extract the correlation between all these forces and solve that sensitivity in this reduced format, you can answer the question more effectively. So that's another application, non-reactive flow. In reactive flow is interesting because there is a computationally enormous problem, and I feel like this kind of reduction is really well suited for that particular type of application. So these days I'm using a lot of combustion problems.
Yeah, because it makes sense. That's where you can make a really big difference as well. Okay, thank you.
Of course.
Yeah, I wonder if shape optimization would be some relevant.
So that's right. So shape optimization, the shape is an infinite dimensional perturbation, right? So I mean, we haven't done that, but we have thought about it. And so I would say if the problem is a steady state, I wouldn't even use this. Adjoint is perfect. If the problem is like a two-dimensional and even low Reynolds number, I think I would still use adjoint because the storage is not a big issue. But if the problem is three-dimensional, moderate Reynolds number, then adjoint could become problematic. And you can compute the gradient of your objective function with respect to the shape perturbation using this approach. So that way the Y coefficient would have the parameter of the shape. The U will show you the sensitivity. And so you can easily compute the gradient using U and Y because you have the full dimensional sensitivity. The nice thing actually here is that in comparison to adjoint is attached to the definition of the objective function. So if you change the definition of objective function, you would have to solve the adjoint equation again. Here, because this is a forward sensitivity, you can actually, once you compute this, you can compute the gradient with respect to any objective function. So that's another advantage. But so I would look at the specific problem and the context and all of that, and then use this technique. But right, yeah. So you could use this in our paper. Actually, we have an example of infinite dimensional perturbation to a chaotic system, and we show that we can track the tangent equation accurately.
I see. Yeah, I'm looking forward to see your future paper. Okay, so last chance for question. Any question for Hessam? Okay, if not, let's thank for the speaker again.
Thank you.
Okay.